Hi, it's Bruce, and welcome once again to my Colorado Rocky Mountain Lab. And what we're going to take a look at today is a little project that I put together here. It's a power meter, an RF power meter that indicates, well, the output is actually in millivolts, but it gives you an indirect indication of decibels, decibel milliwatts, which is an RF output generally. And it's a relatively inexpensive board that I purchased from China on eBay. I don't know, I think I paid maybe 20 bucks for it, something like that. And it stated that it had a 50 hertz to a 3.8 gigahertz frequency band, and that it could change, find the RMS value of just about any complex waveform coming into it, and that it would cover, well, I don't know, something like 65 decibels of range dB-wise. And I decided, okay, well, we're going to put this thing together. We'll cobble it together into a nice little box, hook up a power supply, the cables, the switch, added a 4-digit meter. The results have been really kind of good. So I set about studying the characteristics of this cobbled together meter, and just to see how it performed, whether it would lived up to its expectations or not. I utilized my HP 8640B signal generator up here, which has a calibrated attenuator on the output capable of going from, well, I don't know, plus 10 dBm to about a minus 60 or 80, something like that. I'd have to look at the dial again closer, but more than enough span on this thing to be able to test. So then I graphed everything. What I found when I did the graphical analysis, give you a look at that, is that these units are extremely linear at any given frequency. Now, when you look across a band of frequencies, the output changes with frequency. The voltage that you get for a reading changes with the frequency. So, in order to really utilize this thing fully, you'd need to determine with some kind of a best fit curve just what the relationship is between the voltage on the reading and the frequency of the signal coming in. But anyway, from 10 megahertz, this is 50 megahertz. Okay, there's 100 megahertz. You can see how flat that is. 150, 200, 250, 300, 400. There's 500. So then it became a matter of trying to decide how to characterize the frequency response. So I did a number of different things, but the one that I'm finally settled on is shown here. Here I took the incoming frequencies from 10 hertz, 10 hertz, 50 megahertz, 100 megahertz, 150, 200, 250, 300, 400, 500, and 549, which is the limit of my 8640B. And then I looked at the, kind of like centered the dBm range to a minus 20, and I decided, okay, at each of those frequencies, I'm going to take a look at the voltage coming out at a minus 20 dBm. And I logged those next to the frequencies. Then I, graphed it. And when I did that, then we get this relationship that's here in the chart. So then it was a matter of let's put a trend line through it. And we did that. We picked a polynomial and we took a look at the different orders. I started with a linear. I mean, it's obviously not linear. It's not exponential. It kind of is logarithmic, but there's a lot of error on the middle and high end, so that's kind of bad. Power would also work in there. This is raised to a natural power of e. Or we got the polynomial. So looking at a second degree, like if you were looking at a parabola, kind of fits with a lot of errors. Third order is better, a lot better. Fourth order, we're starting to hit every dot. We missed this one here. That's 50. Fifth order, and then we take a look at the sixth order. So I went for the sixth. We're touching every dot all the way up. So the sixth order equation is displayed down here. I listed the coefficients over here, and then I made my calculation, my sixth order VR calculation, based on that equation and the incoming frequency. So this is the predicted output from that equation. So it says here that I should get 0.799 dBm at 10 megahertz for a voltage of 0.792, and that's off by 0.726 because 0.792 was the 20 dB mark. And then doing the same thing for 50, we calculated that the 1.503 volts that we had at 20 dBm would, in our calculation, would correspond to 1.48 dBm, which was down about 2.7%, 1.8 dBm. And so on. So we went through. So the results are over here. Error-wise, we're under 4% in every case, and we were only at 4% at 100 megahertz. Everything else was under 3. We had at 50 megahertz, we had 2.7%. Then we fell to 1.9, 1.4, and a number of them down in the under 1%ers. So it's a pretty good fit, and a pretty good predictor. So once I'm able to predict what the 20 dBm voltage reading would be, then I'm able to take whatever voltage reading I get at a given frequency, and I could subtract its correlating 20 dBm mark, and that'll tell me how many dBm I am away from it, and then divide that by 0.05 volts, and you'll get the dBms that you've shifted from 20 dBm. Determine your power output to within better than 5% anyway. Now what I found was this thing was listed as being operable from 50 hertz to 3.8 gigahertz, and unfortunately my testing showed that anything below 10 megahertz, you basically could forget it. 5 megahertz, there wasn't any output, and as you went up, it was there, but it was not predictable. So 10 megahertz up, it was good. I suspect that the reason for that is that the capacitors they probably put on the board in the input were too small for the lower frequencies. And but I don't know that for a fact until I tear into this thing more as far as the circuit goes. But 10 megahertz through 550, I'm good. The unit is quite linear in V-read versus dBm at any frequency. Like I mentioned earlier, the output voltage varies with frequency, so you provide this calculation to correlate the two. And here I've got a little calculator where I can put in a given frequency, the voltage reading that I have there, and it'll tell me how many dBm that is. And there's the calculation here. And then you can compare it. If you know the dBm, you can compare it and come up with an error factor. So it was an interesting thing to try, and it worked actually quite well. I don't have any other device that would be capable of reading power, RF power like that. So I'm quite happy to have it, and the whole thing probably ran me, I don't know, $40, something like that, to build. Basically, I'm using a wall wart from an old cell phone as a power supply. So really no investment there. The only thing I really invested in was the board itself and the meter. The rest of the stuff I had on hand. It's really quite repeatable. When it's first cold, when you first turn it on, probably combination of power supply and the board itself heating up, but it takes a few hours for it to completely warm up and stop drifting. You'll wind up in the beginning with a lower reading probably for VR, and then it will slowly climb up a couple of millivolts over the couple of hours time. But this thing's been on all morning, so I really don't have a problem at this point. So there we have a unit that with a little calculation on the side, you can determine your power output. It's cheap and it works well. Now we're going to show you another unit that's very similar, does a similar function, but it does it quite differently as far as the readout goes. So we'll take a look at that in our next video.